All right, so small x physics was mentioned quite a few times throughout these 2 weeks. We are very happy to have Sievert from New Mexico State University, who will actually give us lectures about small x physics. For yours.
Right, thank you very much. It's a real pleasure to be back at the CFNS Summer School and to have a chance to talk about small x evolution. A couple of comments before I dive in. I'm Matt Sievert from New Mexico State University. If you have questions on anything, you're welcome to send me an email. The caveat is that I'm terrible at emails, so I may not reply to you, but that's nothing personal. If you keep sending me emails, I will eventually get back to you. I'm very sorry. The other thing that I should mention is whatever I don't have time to cover today is still drawn from this textbook, which is the textbook that my PhD advisor, Yuri Kovchegov, wrote. So this is the authoritative textbook on small x physics, QCD at high energies. If you look up this identifier on Inspire, we'll at least provide you the publication information so that then you can go find the exact thing. So for further information, you can look there. I also wanted to emphasize, today I'm going to do a Blackboard calculation, and then tomorrow I'll do PowerPoint slides. For the Blackboard calculation, I had to make some assumptions about what you have already seen before and what you haven't. But just in case I go over something that you've not seen before, there's an appendix section in the notes that covers conventions, QCD, color factors, things like that. So please feel free to interrupt me at any point if I say something, assuming you're familiar with it and you're not, but there's other supplemental information in the appendix. Okay. So I guess before I dive on in, I'm going to float back and forth. I think mostly I'll do equations on the Blackboard here, and then I think I'll draw important figures on the whiteboard, and then we can go back and forth. A little bit paradoxically, I'm going to give you the introduction to small x evolution and where all of the pieces come from, but I'm going to hardly talk about x today at all. So let me say a word about x and what that has to do with what I'm actually going to show. The first question is always, what does small x mean? And the answer is there are different meanings to small x depending on the context. For the purposes of what I'm going to show you here today, the important thing about small x is that it is synonymous. It is synonymous with high energy. The simplest way that I can say this is that when most people think about x, they're thinking about deep inelastic scattering. And in deep inelastic scattering, x has a particular meaning. It's Bjorken x, which is defined as q squared over 2 p dot q for DIS. And if I rewrite this in terms of invariance, then this is q squared over, I would call it s plus q squared. Some experimentalists like to call this w squared. This is the, if you like, the center of mass energy of the virtual photon-proton collision. It's also equal to the invariant mass of the final state produced when the virtual photon is absorbed. The connection that I want to make here is just, what does small x mean? The limit of interest is the one where the center of mass energy is going to infinity and q squared is constant. If I take this limit, then as s goes to infinity, s is much greater than q squared. So I guess maybe I'm not being sufficiently precise. I really should say this. S much, much greater than q squared, both going to infinity with the ratio fixed. In this limit, this is approximately q squared over s, and this quantity is much, much less than 1. So there's a lot of physics of x that is specific to DIS, and I'll get into all of that tomorrow. But the essence that I'm really going to talk about, the essence that connects it to QCD, has very little to do with DIS. It has everything to do with QCD at high energies. So the main focus that I'm going to talk about today is a Blackboard calculation in this limit where s is going to infinity and q squared is fixed. And if you think, what does this have to do with x, then keep in mind this pocket formula in the back of your mind. Loosely speaking, in terms of Mandelstam variables, x is a quantity that behaves like t over s. So in the limit s going to infinity with Mandelstam t constant, the momentum transfer, that corresponds to small x. So today I want to do a calculation of high energy scattering. S goes to infinity in QCD, the simplest possible process I can write down, which is quark-quark scattering. And then the next to simplest process that I can write down, which is an NLO correction producing a gluon in the final state. And I want to analyze these two processes in the limit s going to infinity and q squared much less than that, or t fixed, let's say, with s going to infinity. Okay. So as my example calculation, so let's work on quark. Quark goes to quark at tree level. So this is just elastic quark scattering. The problem that I'm interested in is the general amplitude, you could say the S matrix or the T matrix, for a quark coming in with some momentum P1, some spin S1, maybe some color I. And then I see a quark coming out in the final state with P1 prime, S1 prime, I prime. And then I have a second quark coming in with P2, S2, J. And then I see another one coming out, P2 prime, S2 prime, J prime. This is my general blob of an amplitude that could contain anything. At lowest order in QCD, there are exactly two diagrams. One of them looks like this. P1, S1I, P2, S2, oops, sorry. 1 prime, I prime, P2, S2, J, P2 prime, S2 prime, J prime. And then the momentum transfer is something like, how did I draw it? P1 minus P1 prime. This is the diagram that I'm going to spend most of the first part of the lecture computing. In principle, there's also a second diagram that I have to worry about because I have identical particles in the final state. At least if these are identical flavored quarks, then I have a second diagram I have to worry about. If they're distinguishable, say up scattering from down, then this is the only diagram. But if I did have identical quarks, then I would have another diagram I'd have to worry about that would look like this one. That would be a U-channel diagram. I would have to add the two, but then I remember Fermi statistics that these are identical fermions in the final state. So when I swap which one is which, they come with a minus. So this is my basic scattering process. And if I were just computing this cross-section in general kinematics, then I would include both. But I'm not interested in general kinematics. I'm interested in this set of kinematics, which has a particular name known as Reggie kinematics. Let me maybe add this over. So when I talk about Reggie kinematics, I mean S going to infinity with S much greater than T. That's to be contrasted with Bjorken kinematics, which is what we usually think about for deep and elastic scattering. That's the non-small x limit. So if I'm going to attach words to this, Reggie kinematics is the limit of small x, and Bjorken kinematics is the limit of large x. In Bjorken kinematics, your S and Q squared are both large, or S and T are both large. They're of the same order as each other. And these are both going to infinity together. So both of these are technically a high energy limit. Both of them have S going to infinity. But this one has S going to infinity with T fixed, or with T much smaller than S. This one has S and T comparable going to infinity. This is a one-scale problem. This is a two-scale problem. So Reggie kinematics typically describes forward scattering, meaning you have particles coming in with a massive amount of beam energy. They might have a tiny deflection, but overall the scattering angle of particles goes to zero if S is going to infinity. That's the opposite of Bjorken kinematics, where my energy is going to infinity, but the recoil is also going to infinity. That's large angle scattering. Large angle or hard scattering. So a priori, if I'm interested in S goes to infinity kinematics, I have two diagrams to worry about, but I'm actually going to only need to calculate the first one. Why is that? How do these diagrams depend on S, T, or U? So this first diagram, for instance, has a propagator here carrying momentum P1 minus P1 prime. Which Mandelstam variable does that correspond to? T. So Mandelstam T is P1 minus P1 prime squared. This amplitude is a T-channel amplitude because the propagator goes like 1 over T. And for me, t is a small number. T is not nearly as big as s. This diagram is not dependent on t. If I label the incoming and outgoing momenta, so if this is P1, the one that it connects to is P2 prime. So the momentum transfer here is P1 minus P2 prime. So that Mandelstam variable is not t. What is it? U. So my IMU channel is going to have a propagator that goes like 1 over U. And then what is U doing in this limit? I talked about S and T. There are 3 Mandelstam variables, S, T, and U. Why didn't I talk about U? Because U isn't independent of the other ones. I have S plus T plus U is a sum over all of the masses. For the simple example that I have here of identical quark-quark scattering, then I get 4m squared. So U is 4m squared minus S minus T. And S is going to infinity. T is constant, the mass is constant. So in regikinematics, U is basically negative S, and it's going to negative infinity. That's why I don't have to worry about the U channel diagram. If I have infinite energy at the LHC coming together, mostly I have forward scattering. It would be very weird if I had back scattering. That's energy suppressed. And that's what we conclude. So what I find is I actually don't need to worry about this one. This is a power suppressed correction. It scales like 1 over S as S goes to infinity. So no number of alpha S's can compete with the suppression of 1 over the energy at the LHC going to infinity. So this is a very general reason why I should throw away U channel and then compute T channel scattering to high accuracy. So that's the main goal. So the next thing that I want to do is just compute this amplitude in detail from the Feynman rules of QCD. Any questions before we start? Okay. So let me just apply the Feynman rules. It's very fragile chalk. So if I'm just doing everything at the elementary level, the diagram that I'm computing there is my T channel diagram, which is actually I times the scattering amplitude because the S matrix is 1 plus IT. On the right-hand side, I can start filling in all of my elements. So I have an external spinner associated with the particle P1 prime. So that is U bar, let me call it 1 prime for compactness so that I don't have to write P1 prime S1 prime 100 times. Right after that, there's a vertex. In QCD, the vertex is IG, the color generator TA. So the Gell-Mann matrix divided by 2. If you need a reminder of what those are listed explicitly in the appendix. TA is a matrix, and I'm talking about a specific color element of that matrix. This is the color matrix. Let's say if at this vertex, the gluon has color A, then this is TA. Final color is I prime, initial color was I. So I'm talking about a very specific element of that matrix. So this is TA I prime I, gamma mu. And then I have U1 to complete the spinor product. I have another spinor product on the other side. That's U bar 2 prime, another vertex, IG. A priori, let me call it TB, but in a second, I'm going to put B equals A. And this will have indices J prime J. And again, let me give it a generic index nu for the moment, but in a moment, I'm going to put upper mu is the same as lower mu. That's the spinor product part. The other thing that I need is the propagator. In Feynman gauge, which is the simplest way to compute this, the propagator is just minus I G mu nu, coupling these 2 vertices, and then a Kronecker delta for the colors of the gluon, divided by the momentum transfer, which in this case was T. If you like, there's a plus I epsilon. There's also minus M squared. No, there's no M squared for the gluon. So in principle, you have a plus I epsilon, but since we're not computing loops, the I epsilon is not relevant. We can just drop it. So this is my basic building block. I have, let's see, 1, 2, and then get rid of one of them, factors of I. So I get a single factor of I. I have two factors of G. My propagator has a 1 over T. My overall color matrices are TA, I prime I, TA, J prime J. And then I'm left with the kinematic spinor product U bar 1 prime gamma mu U1, U bar 2 prime gamma lower mu U2. This amplitude, by the way, looks like exactly what you would have had in QED, aside from the presence of the color matrices. So I would have exactly the same answer if this was a photon. I would just change the numerical factor in front. The kinematic dependence is identical. So I have my T channel amplitude, my U channel amplitude that goes along with it, I can replace with 0 at leading power in the center of mass energy S. I could then do all of the usual QFT techniques of take the amplitude, square it, convert the spinors to traces, convert the traces to dot products, convert the dot products to Mandelstam variables, and then take the Regge limit. S goes to infinity, T equals fixed. That will work, that's fine, but that's only really possible for a very simple diagram like this one, and it will not be a good strategy going forward. Instead, it's highly advantageous to simplify at the amplitude level, using these kinematics now before we square it. Probably people can't see if I write in this panel, right? So I should go back here? Yes, okay. So the real simplification happens in the spinor product. So I need to look carefully at what happens to U bar gamma U as a function of its momentum. Thankfully, there's a general expression for U bar gamma U, no matter what the momentum is, which is called the Gordon identity. So in general, U bar of P1 prime, S1 prime, gamma mu, U of P1, S1 can be decomposed as U bar P1 prime, S1 prime, U P1, S1, and then in between I have factors. One factor is P1 plus P1 prime mu over 2m. This one multiplies, if you like, the identity matrix. And then there's a second term which depends upon the momentum transfer. This one is I sigma mu nu P1 minus P1 prime mu over 2m. This sigma mu nu is the commutator factor of I. It's the commutator of gamma matrices. So this is a general result which is known in quantum field theory. If I were doing a full exact kinematics calculation of this amplitude, then I would have both pieces and they would both be equally important. But I'm not looking at this in general kinematics, I'm looking at it in Regge kinematics. And in Regge kinematics, P1 and P1 prime are very, very similar. Regge kinematics, S going to infinity tells me I have a huge amount of energy of the incoming quark. Most of that energy is still going out in the same direction in the outgoing. The easiest way to specify the kinematics is using light front coordinates. I'm assuming by this point in the summer school that you have seen light front coordinates at least once or twice. Is that true? Sort of. These are also defined in the appendix. If you need a refresher, let me write these down now. The point about light front variables is that they're really useful for describing high energy scattering. Light front coordinates. You sometimes hear it referred to as light cone coordinates, but I think Stan Brodsky is technically right that you're describing propagation along the fronts, not propagation along the light cone. In light front coordinates, we define, let's say, P plus, the momentum going along the plus z axis at the speed of light, is defined as 1 over square root of 2 P0 plus P3. So in ordinary variables, this is 1 over square root of 2 E plus PZ. Why do I care about this thing? Because if my particle is moving at the speed of light in the z direction, PZ and E are basically the same thing. On the other hand, the reverse combination called P minus 1 over square root of 2 P0 minus P3. So that's E minus PZ. If my particle is going along the positive Z axis, then this is the one that's large. This one is approximately 0. So the point is that high energy scattering has very simple kinematics, and the easiest way to describe that is in terms of how much momentum along the positive Z-axis at the speed of light, how much along the negative Z-axis at the speed of light, and transverse is still transverse. So this is a powerful way of expressing the kinematics. I'll write it down in vector components. So I'll mention, by the way, I'm using the standard 1/√2 convention for the light front coordinates. Sometimes you'll see people define it without the square root of 2 or with something else. You can do it that way, but then crazy factors propagate through the entire calculation, and I don't advise it. So I guess the point is that when I have an on-shell condition, so let's say I have an on-shell particle. So p squared equals m squared, and I want to know what does that tell me in terms of my light front coordinates. Well, I have to expand my dot product. If I have a product of two vectors in Minkowski coordinates, this is p0 q0 minus p dot q. I could take these equations and let's say solve it for p0 in terms of p plus plus p minus, or p3 in terms of p plus minus p minus. And if I do that and substitute it into this expression, what I get is p plus times q minus plus p minus times q plus minus p perp dot q. Basically, I just decompose the time-like piece into a sum of light-like pieces, and I end up with a combination of however much momentum along the plus z-axis times the momentum along the minus z-axis in either. So if I have an on-shell particle using this condition, p squared equals m squared, and p squared is equal to 2p plus p minus minus p perp squared. So this is just a choice of coordinates for my vector. If I have a momentum vector, not all four components are independent. My on-shell condition fixes one of them in terms of the others. Usually in Minkowski coordinates, we fix the energy in terms of the spatial momentum. Here, it's a little more democratic. I could solve this equation for p minus or p plus in terms of the other. So for example, I could solve this and get p minus equals p perp squared plus m squared over 2p plus. Or I could equally well solve it for p plus and call it p perp squared plus m squared over 2p minus. Either way, I only have three independent components, p perp and one of the light cone components. The on-shell condition fixes the other. So this is extremely natural for talking about a particle with a massive amount of light cone momentum in a specific direction. So if my quarks here are colliding along the plus z and minus z axis, one of them has a huge p plus and a tiny p minus. The other one has the reverse, a huge p minus and a tiny p plus. That's the kinematics at work. So for my incoming particles, P1 mu, a priori, its components are, it has, let me choose P1 to be going in the minus direction. So let's say P1 minus, the light cone plus component, I'll solve as P perp squared plus M squared over 2P1 minus. In general, I could have a P1 perp, but that's up to me. I choose the frame my collision is happening. Usually I choose a center of mass frame of some kind where P1 and P2 are coming straight at each other and not along some crossing. So by simple frame choice, I can pick P perp equals 0. And let me choose my coordinates here, choose my frame of reference, such that P2 has a large component along the light cone plus direction, and P1 has a large component along the light cone minus direction. That seems a little backwards sometimes. Normally when one does that calculation, you like to put the plus at the top and the minus at the bottom. I'm doing it this way for the analogy to deep inelastic scattering. Tomorrow when I talk about deep inelastic scattering, I'll have a photon probe up here, and the proton will be down here. And we normally talk about PDFs as a fraction of the plus moment. So if it seems backwards, that's why, to make the comparison with DIS a little more straightforward. So if I choose these conventions in my limits, okay, so P1 is this. P2 has a large P2 plus. Its minus momentum is on shell. So this is now just m squared over 2p1 minus. This is now m squared over 2p2 plus. 0. And the limit that I care about here is the limit in which s is going to infinity. S is p1 plus p2 squared. And the limit that I'm interested in is going to turn out to be the one where p plus, p2 plus, and p1 minus are both becoming very large. So if I compute this dot product, then this is approximately 2p1 dot p2. And this is approximately 2p1 minus p2 plus. So if I'm in a strict center of mass frame where p1 minus is exactly equal to p2 plus, usually I don't need them to be exactly equal, but just to orient your head around this. In a strict center of mass frame, they're both equal to each other and they're both equal to root s over 2. So this is sort of what I have in mind. I'm computing the scattering in the limit p1 minus is of order square root s going to infinity. p2 plus is also of order square root s going to infinity. And in this limit, these momenta simplify tremendously. This is approximately 0 in the plus direction, a like momentum in the minus direction, and nothing per. This one is something in the plus direction, nothing in the minus direction, nothing in the per direction. So this is the high energy Reggie kinematics. I'll also use the word iconal associated with this. Iconal means leading power in S, which also means it's leading power in Bjorken X. So this is what I'm interested in. I want to apply this to the Gordon identity. So these were my initial particles. By the same reason for my final state particles, let's say P1 prime mu. P1 prime has a large minus momentum, P1 prime minus. It has some perp momentum, P1 prime perp. But its plus momentum is on shell. P1 per prime squared plus m squared over 2 P1 prime minus. And again, I have a huge amount of minus momentum coming in from the projectile. Momentum conservation says it has to go somewhere. This is where it goes. It comes out along the light cone minus direction of P1 prime. And that means that P1 prime looks an awful lot like P1, right? If P1 prime is going to infinity, then my first component is small. My second component is large. But now I have a small amount of perp momentum. My P1 had huge amount of energy along the minus direction. P1 prime also has a huge amount of energy along the minus direction. The only difference is that it has a small amount of transverse momentum. Again, if the only thing that I care about is the leading power in square root of s, this is the only component I care about, and I can ignore the component here, which is transverse. That's where my simplification happens in the Gordon dynamic. So what I had was u bar 1 prime gamma mu u1 is u bar 1 prime p1 plus p1 prime mu over 2m plus I sigma mu nu p1 minus p1 prime nu over 2m u1. And the point is that my P1 mu is approximately the same thing as my P1 prime mu at leading power in square root of s. If I take just the leading power, then I'm just taking this part. That's something that only has a component in the minus direction. And the component in the minus direction it has is the large component P1 minus. And then the error in this approximation, let me write it this way, 1 plus order P perp or m over P1 minus, which is just square root of s. So what I'm saying is that to leading power in square root of s, the only thing here is just a light-like momentum along, in this case, the minus c axis. And if that's the case, then this difference here is small. P1 is approximately the same thing as P1 prime. In this strict limit, this term is completely 0. And these two are identical. So what I get is something extremely simple. I get 2 P1 mu over 2m, u bar 1 prime, u1 with no matrix in between. This is constrained by the normalization of the spinors. This is 2m delta S1 prime. The two M's cancel, and I get 2p1 mu delta S1 prime. And if I want to be even more explicit, my p1 mu is only along light cone minus. So this is 2p1 minus delta mu minus delta S1 prime. This is a massive simplification where we said the only thing that matters is that I have a huge amount of light cone momentum along the positive, in this case, the negative z axis. And so I just get one term from the coordinate. For exactly the same reasons, if I compute the other product, u bar 2 prime gamma mu u2, I get the same answer, but now dominated by the momentum along the plus direction. So I get 2p2 mu delta S2 prime, which is 2p2 plus delta mu plus delta S2 prime. That was the only complicated part of my amplitude. I had to just evaluate the spinor products. Again, this part would be exactly the same if I were doing QED instead of QCD. This is just high energy kinematics. So now I plug it all back in. So I had I g squared over t, ta I prime I, ta j prime j. And then now for my spinors, I plug in, let's see, so I have 2p1 minus delta mu minus times delta S1 prime, 2p2 plus delta in this case, this is lower mu delta S2 prime. And then these two things combine together, 2p1 minus and 2p1 plus. This is 4p1 minus p2 plus, which is 2 times the center of mass energy S. So if I pull everything out, I get a factor 2i g squared, color factor, ta I prime I, ta j prime j. And then from the kinematics, I get S over, and then the Kronecker deltas for the spins. So the key thing here was this factor, the kinematic dependence of the scattering amplitude. The denominator goes like 1 over t. We knew that from the beginning by the propagator. The thing that was maybe not obvious was that the numerator scales like s. So that as s goes to infinity, the numerator is blowing up. It's becoming large. And this s will ultimately cancel in factors with the cross-section, the flux factors of the cross-section. So this is my expression for the scattering amplitude. And the corrections to this are down by powers of some perp momentum over square root s. So this is the leading behavior as s goes to infinity. Now let's compute it to a cross-section. To compute it to a cross-section, I need to compute the amplitude squared averaged over quantum numbers. So that's not just take the absolute value square of this thing. That's simple. That's 4 g to the 4th s squared over t squared. The more complicated part is that I have to sum over all spins, and I have to sum over all colors. And I'm not just summing over the quantum numbers in the final state, I'm averaging over the quantum numbers that came in the initial state. So from the spins, I have 1/2 squared because I have 2 quarks that have spin 1/2. For the colors, I have NC number of colors. For QCD, we have 3 colors. But it turns out to cost me almost nothing to consider not 3 colors, but a general number of colors, NC. Ultimately, one of the nice tricks that we can use is pretend that NC is large. And in an expansion for large NC, actually the color algebra simplifies tremendously. So that's what NC is. For me, I'm going to put 1 over NC squared because I have NC number of colors for P1, NC number of colors for P2. And then I have to sum over all of these things. And now I have the square of this. My color factor is TA I prime I, TA J prime J. When I complex conjugate it, I get TB I prime I, TB J prime J conjugate. But these are Hermitian matrices. When I take the complex conjugate, that's equivalent to transposing the indices. So when I take the complex conjugate, I switch I and I prime, J and J. And I still have delta S1, S1 prime, delta S2, S2 prime. So summing over the spins is easy. When I sum over, let's say, S1 prime and S2 prime, I kill the delta functions. Then I sum over S1 and S2 and I get a factor of 4. The 4 exactly cancels the 1/2 and 1/2 squared. So the sum over spins is easy. The sum over colors is also easy when you're familiar with it, but you may not be familiar with it. If you look at the color structure that has appeared here, then you notice that I've formed actually traces of the color matrices. So this color factor is 1 over NC squared. TA I prime I, TB I prime is a trace of TA TB. And similarly, the other factor is a trace of TB TA. If you've worked in QCD, then you probably have some of these color identities memorized, like I do. If not, they're listed in the appendix of the notes. One nice identity is a trace orthogonality condition between the generators, the same way the Pelly matrices have. You take trace of sigma I, sigma j, then you get a delta ij. In the same way, trace of TATB is 1/2 delta AB. When I plug that in, I get 1 over 2 NC squared. And now I have a single trace of TA times TA. So this TA is an invariant of the color algebra. So think of it like rotations in 3 dimensions. So my generator is the angular momentum J. An invariant of the rotations is J squared. It's a scalar. It doesn't transform under rotations. That's a general property of all Lie groups. So in the same way, if you think of TA as a vector with component A in color space, TA summed over A is the absolute value squared of that vector. Like J squared, it's an invariant of the algebra. It's called the quadratic Casimir. So TA is a number called the quadratic Casimir factor times the identity matrix. That number for the Casimir is NC squared minus 1 over 2NC. So I'm saying this is just a number, and I pull it outside, and then I get trace of 1. Trace of 1 gives me NC, the number of colors that I have. So that allows me to compute the full color factor. So my 1 over NC squared trace TATB, trace TATB, it doesn't matter what order, is CF over 2NC. I get a 1/2 from the trace. I had 1 over NC squared to begin with. I get a second factor of NC from trace of identity. And this is my color factor that comes up. So at the end of the day, I get M squared averaged over all quantum numbers is 4g to the 4th S squared over T squared times the color factor CF over 2NC. I'm almost done computing the cross section. The last thing that I need to compute the cross section is to plug this back into the formula from Peskin and Schroeder. That's 1 over 2 E1 to E2, absolute value V1 minus V2, amplitude squared, momentum conserving delta function times 2 pi to the 4th. And then I have a phase space for each of my final state particles. D3 P1 prime, 2 pi cubed 2 E1 prime, D3 P2 prime, 2 pi cubed 2 E2 prime. As usual, I've got too many phase space factors here, and most of them are not independent because they're constrained by the delta function. If I, let's say, integrate over P2 prime, I have 3 components. I use the delta function to fix all 3 components of P2 prime in terms of the others. There's still 1 component of the delta function left. That's the energy conserving delta function. Maybe for the sake of time, I'll write the answer for the cross section without actually going through the algebra to pick up those poles. Or rather pick up the delta function. So the final answer is a sigma D2 P perp prime is, 4 alpha S squared CF over 2NC, 1 over P1 perp prime to the 4th. And you can basically see where all of these factors come from. The color factor is still there. This is 1 over T squared. We had 1 over T in the amplitude. This is 1 over T squared. The factor S squared in the numerator canceled against 2 factors of the energy in the denominator. So 2E1, 2E2 is basically 2S. That cancels 1 factor of S. E1 prime times E2 prime is also basically S. That cancels the other factor of S. So I end up with just 1 over T squared for the overall scale. The last thing that I can do with this is convert this to a total cross-section. So this is a total cross-section evaluated at leading order. Also, since I'm just calculating elastic QQ to QQ scattering, I could also consider this just the elastic part of the cross-section's leading order. And that's just this answer integrated over all T. In principle, I should integrate over everything. If you stare at this integral, you'll realize immediately that if you integrate it down to PT equals 0, you're going to have a divergence. That divergence is an artifact of the fact that I've just considered elementary quark-quark scattering. If instead of a bare quark, which has unshielded divergences, I had a dipole or a proton or something that has a physical scale to it with color confinement in it, then I wouldn't expect to get this behavior. I expect that in real life, this is going to be cut off below by something of order the mass. So let me just put in a cutoff. I'll call it the mass for simplicity, and then I can do the integral trivially, and I get 4 pi alpha squared CF over 2MC, 1 over M squared. The cross section is dominated by the infrared, so the lower momentum is what sets the number. Okay. This is the first major result that I wanted to get to, the elastic quark-quark scattering cross section. Important features about this are that it is unsuppressed at high energy, right? So this behaves as S to the power 0 as S goes to infinity. The reason it behaves like S to the power 0 is because it's mediated by gluons, vector bosons. That vector coupling was critical. It gave us a factor of S over T. If it was not a vector, if I was doing Yukawa theory instead, then I changed the numerator properties and I'm going to sacrifice factors of that S. So if instead of gluons, I had some other theory, like cube theory, Yukawa theory, whatever you want, everything else other than gluons, other than vector bosons, is going to be power suppressed as S goes to infinity. Something mediated by gluons, however, is leading power. The only thing that limits this is the number of alpha S's, and alpha S is not a particularly small number in QCD. So that's an indication that you're going to have to worry about not just one such scattering at high S, but potentially many such scatterings. And this will lead us to resum those scatterings into a Wilson line. We'll talk more about that tomorrow. Questions so far? Okay. Let me see what I can show you out of the radiation calculation in the time that we've got left. Alexei, could you please scroll to the diagrams? That will save me some time. Thank you. Okay. So the next thing that we want to look at is now what happens if I have an NLO correction to this process, specifically a real radiative correction that produces an extra gluon in the final state. A priori, there are 5 ways in QCD that I can do that. I can have final state radiation off of the P1 particle, initial state radiation off of the P1 particle, or initial and final state radiation off of P2. And then the last case is interesting. This one is uniquely non-abelian. It only happens in QCD. This is the one where the T-channel gluon undergoes gluon-Bremsstrahlung because it is itself charged. Aside from the last diagram, everything else is a counterpart in QED. So we can think about QED or QCD at the same time. We just drop the color factor or the color matrices here, and we drop diagram E. So now I want to calculate in detail diagrams A and B. Diagram C and D I'll be able to get for free by reflection of my answer from A plus B. Diagram E requires some work, and we don't have time to go through it here. I will just quote you the final answer. So if I set up the calculation again, let's say for diagram A. So now if I construct the diagram, I start off with U bar 1 prime. Then I have an emission vertex. The emission vertex is IG TA epsilon slash star of, in this case, momentum K and polarization lambda. I think, could you go to the next figure, actually? I show A and B in more detail. Thank you, here. So if I choose the color of the radiated gluon to be color A, then that tells me I should put TA at this vertex. I'm going to have a TB at these vertices, which is summed over B, but A is free and fixed because that's the color of the final state gluon. So that's this vertex. After this, I've got a propagator. This is a quark propagator. For diagram A, it's P1 minus Q. If Q is this momentum transfer, I come in with P1, I subtract Q from it, and then P1 minus Q branches. So with this diagram, P1 minus Q is the intermediate propagator. So that brings I P1 minus Q slash, in principle, there's a plus M that I'm going to neglect. In the denominator, I'm going to have P1 minus Q squared. And again, there's an M squared that I'm going to neglect. And then I have the scattering vertex. The scattering vertex is IGTB, gamma mu, gamma mu. And then U1. And then I have the spinor product from the other side, which is still U bar 2 prime, gamma lower mu, U2 times IGTB. And then divided by the propagator, which is Q squared. So I think I have, the propagator is minus I. So I think now if I've got it, I've got -1, 0, +1, +2, +3 factors of I. So that's I cubed, which is minus I. I have 1, 2, 3 factors of G. My denominator is Q squared, P1 minus Q squared. And then I have, let's write it this way. TA times TB together has overall indices I prime I. That's the color rotation of the upper line. And then I have this color matrix TB acting on the lower line, J prime J. And now I have my spinor product, U bar 1 prime, epsilon slash K lambda star, P1 minus Q slash U1 times U bar 2 prime. I dropped the gamma. Gamma mu 1, gamma mu U2. Prime epsilon slash P1 minus gamma. Yes, okay, good. Before I do anything to this amplitude, let me write right next to it diagram B, because they're very, very similar. Diagram B has almost all the same factors as diagram A, but there's 2 differences. One is that the order of the vertices is different. In this diagram, when I read from right to left, first I see the TA for emitting the gluon. Then I see the TB for the scattering. Here they happen in the other order. First I see the TB for the scattering, then I see the TA for the emission. So those vertices are reversed. The other thing that happens is because the vertices are reversed, the momentum of the propagator in between is also reversed. Here it was P1 minus Q. Here it's P1 minus K. Aside from that, the diagrams are identical. I get minus I G cubed, Q squared, P1 minus K squared. Now I have TB TA I prime I, TB, J prime J. And now I have U bar 1 prime. Now the gamma mu comes first. Now the gamma mu comes first, then the P1 minus K, then the epsilon slash, and then U1. Again, I want to simplify these expressions at the amplitude level first, using Eikenel kinematics. We already know how to do that for this factor. That's going to make my life immediately much easier. If I take this factor and replace it with 2p mu delta S2 S2 prime, or equivalently, I could just call it 2p2 plus delta mu plus delta S2 S2 prime. I can plug that in here. Once I know the value of mu in this product, that also sets the value of mu in the other product. So if I know that this one has the P2 plus, that must go along with a gamma minus in the other trace. So I get minus I G cubed times 2 P2 plus delta S2 S2 prime Q squared P1 minus Q squared TA TB TB. Now I have U bar 1 prime epsilon slash P1 minus Q. If this one was gamma upper plus, then this one is gamma upper minus. Q1. And similarly over here, minus IG cubed, Q squared, P1 minus K squared, TB, TA, TB, 2 P2 plus, delta S2, S2 prime. Now I have U bar 1 prime, yes, gamma minus, P1 minus K, epsilon slash. So the other thing now I need to look at is how to simplify this more complicated numerator algebra. I can simplify this by using the Dirac equation. So for instance, let me look at this one. This product here has something very large in it. This has a momentum of order square root s. Specifically, that's P1 plus gamma minus entering this product, plus small stuff. This is the largest component if I can keep it. This one has gamma minus. So if I'm looking for the largest plus, the largest momentum here, I've got P1 plus, U bar 1 prime gamma minus, gamma plus, epsilon slash. And the other thing that I can use to simplify this expression is the Dirac equation. The equation of motion for my P1 spinner is, sorry, I got this backwards. It's P1 minus gamma plus. Now that's correct, minus gamma plus. So the Dirac equation says P1 slash minus M on U1 is equal to 0. And in my high energy kinematics, this left-hand side is basically just P1 minus gamma plus U. So this tells me at leading power in S, gamma plus times U1 is equal to 0. So that means in this product, my gamma plus is sitting almost next to the U bar. That would give me 0. If I take this and I anti-commute it past, I will get 0. So that allows me to replace this with an anti-commutator for free, because the term that I'm adding to make the anti-commutator is 0. And then when I do that, I just get a factor of 2 from the metric. And then everything simplifies tremendously. Let me see if I can continue simplifying these at the top of their respective boards. Okay, so I've pulled out a factor of 2. So then I get minus 4i g cubed p2 plus, and then I pull out a p1 minus from this inner product. My denominator is q squared p1 minus q squared TATB b. And now what I'm left with is u bar 1 prime. Then I have epsilon slash star u1. Again, there's a delta S2 prime. And then the last step is we also now know what this product is. This was 2p1 minus epsilon k lambda star. Because this is the largest component of that spinor product, and if p1 minus is here, then it only talks to the epsilon plus component of the polarization. So now let me put these two amplitudes side by side and stare at what they tell me. 2p1 minus p2 plus is s, so this is minus 2s. Yes. And then I have epsilon star plus times p1 minus. Yes, because this is going to cancel this. TATB, TB, delta S1, S1 prime, S2, S2 prime. Did I screw something up? Oh, TBTA for this diagram. Sorry, thank you. No, it's. Oh, I'm looking at the wrong formula in my notes. This one is TATB. Sorry. Yeah, this one is T.
MA.
Oh, because I wrote the wrong damn thing. Sorry. I'm trying to do A on the left side and B on the right side. Sorry. So that's the point of all of this, is that these diagrams are almost exactly equal in terms of their kinematic dependence. So IG cubed, Q squared. This one is P minus K squared. Now this one is TBTA, TB, and then everything else is this epsilon K lambda star plus P1 minus times factor of 2 and S. Okay, so in my remaining like 2 minutes, let me now tell you what the important part of this expression is. So when I compare these two things, the main kinematic dependence comes in here, in the differences in the denominators. This was P1 minus K or P1 minus Q. So P1 minus Q squared, due to the largeness of P1 minus, is approximately minus 2 P1 minus Q plus. For the same reason, P1 minus K squared is approximately minus 2 P1 minus K plus. Now, K is one of my external particles. I measure the gluon with some momentum K. So K plus is just determined by wherever I measure the gluon. But Q is an internal momentum. Q is fixed by the momentum transfer. So the T-channel gluon being exchanged. So the momentum of Q is fixed. If I write down the momentum Q in terms of, if I write down Q in terms of the other components, let me save you the algebra and just give you the answer. Q mu is approximately negative K plus. Q perp squared over 2p2 plus, which is small, Q perp. So I have two denominators. They have the same P1 plus. The only thing that's different between them is the minus component, sorry, the plus component, whether it's Q or K. And those differ by a minus sign. So this virtuality is plus 2 P1 minus K plus. This one is minus 2 P1 minus K plus. That's physics. They differ by a minus sign because the intermediate propagator is time-like in one case and space-like in the other. You can see that the plus momentum is flowing in one direction and the minus is flowing with it, giving you something time-like, or the plus goes one way, the minus goes the other, and that product gives you something space-like. So that minus sign difference between them is very real. So if I plug this in, let's say this denominator here is 2p1 minus k plus. This one is negative 2. Let me write it here. Negative 2 p1 minus k plus. With that, the kinematics of these diagrams are identical. And if it weren't for these color matrices, they would just cancel each other. So if I'm talking about QED with no color matrices at all, diagram A plus diagram B is 0. Working just to leading power in the center of mass energy, I get nothing. But I don't get nothing for QCD. Even though the kinematics are identical, what happens in QCD is when I subtract these things, I have a difference, TA, TB minus TB, TA times TB. This is not 0. In QCD, this is a commutator of TA with TB. And that commutator generates the structure constants I, F, A, B, C, T, C. So this is a crucial point that if you were asking about how much photon radiation do I get in ultra high energy collisions of two electrons, the answer is 0. And the answer is really easy to understand because if I have infinite energy coming into my electron beams, they don't deflect. The scattering angle goes to 0 if S goes to infinity with T fixed. And if the charges don't deflect, they don't accelerate. You have to accelerate a charge to make it radiate power to infinity. So there is no net photon production in ultra high energy electron-electron scattering in Reggie kinematics. But there is in QCD a massive amount of gluon radiation that comes out because specifically of the non-abelian properties of the theory. I think maybe I'll just tab through the next couple of slides if that's okay with you. Yeah, so here's sort of the discussion. The amplitudes are almost identical. They have identical kinematics up to a minus sign. I didn't discuss the kinematics very carefully, but if I'm producing the gluon at mid rapidity, everything has this 1 over K plus in it. If K plus is as big as P plus, then that gluon is going in the forward direction. This would be a small amplitude. But if I'm looking at gluons coming out at mid rapidity, K plus is small, then that's a large number. K plus much less than P plus. So the amplitude to radiate a soft gluon, much softer than the P plus and the P minus in the problem, is parametrically large. QCD loves to radiate soft gluons. We also see that the spin dependence that comes out of it is trivial. If you ask yourself, what happens if I take S to infinity? You're never going to find any interesting spin physics questions there. If you want to find interesting spin physics questions there, you have to go beyond the Eichenal limit. You have to look at 1 over energy corrections that are power suppressed corrections in this form. But just in the leading power behavior, spin is trivial. We talked about the amplitudes differing by a minus sign. We talked about the color matrices. That means in QED they cancel. It's also very nice. You see, because of the large P minus in the problem, the P minus at the vertex couples to epsilon plus in both diagrams. That gives you a hint that you can strategically choose a gauge that would get rid of those diagrams if you want to. Could you scroll back to the 5 diagrams, please? Thank you. Yeah, so in general, there's 5 diagrams, and in a general gauge, you have all 5. But this suggests if I work specifically in, say, epsilon plus equals 0 gauge, I would kill the contribution of these diagrams. In this gauge, I'm going to reshuffle the weight that used to belong to those amplitudes down into these amplitudes. In the same way, if I picked epsilon minus equals 0 gauge, that light cone gauge, then these diagrams would be 0. And I would put all of the weight in A, B, and E. In a symmetric gauge like Feynman gauge, everything contributes at the same order, and then I can take my answer for A and B and just switch plus and minus and immediately get C and D. I've not explicitly computed E, but it's very instructive that when I add A and B together, the structure that comes out looks like it's got the 3 gluon vertexes. It generates the structure constants, FABC. And FABC is exactly what appears at this trigluon vertex. So when all the dust settles, you add up A plus B, they start to resemble this. C plus D, they start to resemble this. Everything together has the structure that looks like the pure 3 gluon vertex, but with a different momentum dependence. It's a very compact notation that I can sort of fold everything together and write it as an effective non-abelian vertex called the Lipatov vertex. So the takeaway message then, if you'll scroll forward, please. Okay, again. Again. Thank you. So the top amplitude up there, 1.41, that's the expression adding everything together, the 3 gluon vertex as well as all of the other 4 diagrams. If you take that amplitude and you square it, then you get this amplitude squared or correspondingly this cross section. This is a triple differential cross section in the gluon kinematics. It's transverse momentum and its rapidity. This one's also differential in T, the momentum transfer. This cross section is related to a gluon distribution. I could call it a gluon multiplicity, the number of gluons that I'm actually creating in the final state. So for instance, I could take this and integrate over the momentum transfer to get something that looks like a distribution of gluons per unit K perp and per unit Y. Again, I cut off in the infrared by something of order the mass. So I get a simple expression for my gluon distribution. And I can take this distribution and normalize it, dividing by the elastic cross section that we computed first. Then this quantity has units of area over K perp squared and rapidity. If I divide it by sigma elastic, I get something that has units of number per phase space. So this is a multiplicity. It has an interpretation of a number distribution of gluons that you create. If I just take this expression and divide by the lowest order cross section, then I get something dimensionless. And now I can talk about how many gluons are created by this process. The really crucial part that comes out of this, the specific KT dependence is interesting, but not super important. The crucial part is that the right-hand side is a constant. It is independent of the rapidity variable y. That's completely robust. Next page, please. Thank you. So I can take that and run with it. If I integrate over K perp, then I get a number for the number of gluons per unit rapidity. Number of gluons per unit rapidity is a constant. The specific constant here is a consequence of the model theory that we used. And then if I integrate that constant over all of the rapidity of the collision, then I get my estimate for the total number of gluons expected. And it's just that constant times the total rapidity of the collision. How big is the total rapidity of the collision? Well, the rapidity is a log of P plus over P minus. And if I subtract those two things together, I get combinations of P1 minus and P2 plus. That's S. So if I plug this in and I churn all the way through, my difference in rapidities is a logarithm of the center of mass energy. So when I plug that back in, my total number of gluons is a constant times a potentially large logarithm of S. As S gets large, the number of gluons that I'm creating in this process also becomes large. That comes because of the large rapidity, the large phase space where the gluon could have come out, anywhere in between the large P plus and the large P minus of the problem. Okay, next page, please. So various features of this calculation are artifacts of the simple model that we used. They're mass scales that I put in to cut off the infrared and avoid these divergences. If you replaced it with a dipole or you replaced it with a proton or something else, those details would change, especially the infrared behavior of the momentum. But the piece that's completely robust is the rapidity independence of the answer. So for instance, if instead of computing quark-quark scattering, you did glue-glue scattering, you did the entire problem over again, you would find the same answer. Number of gluons produced per unit rapidity is alpha S times a constant. You get a different constant. And that means the number of gluons total is alpha S times a log. It's a constant. This is the origin of small x evolution, because in a strict perturbation theory, alpha S is supposed to be small. Every higher order in alpha S is smaller than the one that came before it. And that's true. Alpha S is small, but it's multiplying a log that could potentially be large. And as S goes to infinity, that log gets larger and larger until it starts to compete with alpha S. That radically changes your perturbation theory. The first thing that we did was sort of take S to infinity in the kinematics, and we got light-like kinematics. That's kinematically small x, or kinematically high energies. That's when you satisfy the Eikenl approximation. This is an even more stringent condition. S is not just much, much bigger than m squared. Log of S is much, much bigger than log of S over m squared is much, much bigger than 1. So that is an exponentially large center of mass. In that limit, I start to reorder the perturbation series, and I break the usual power counting of perturbation theory. This was a next to leading order result with one factor of alpha S in it, and I didn't calculate anything with 2 alpha S's in it. That's been neglected. But if my log starts to become large enough, then the thing that I calculated starts to become comparable to the thing that I neglected. Or the thing that I neglected can become comparable to the thing that I counted. So the point is that the large log upsets the power counting, and you have to do logarithmic resummation. I saw something along those lines on the board when I first came in, so perhaps you guys have seen some version of logarithmic resummation in the past. This is the logarithmic resummation that gives you small x evolution. It's logs of the center of mass energy, which correspond to logs of 1 over x. So I guess the setup that I wanted to get to for tomorrow is this. Alpha S is much, much less than 1. Log S over m squared, in terms of DIS kinematics, is like log 1 over x Bjorken. This can be much larger than 1. And in the limit when alpha S times a log of 1 over x is itself of order 1, that's the breaking point in my perturbation. If I'm below this, the log is not so big that it spoils perturbation theory. Once I hit this, I have to reorder the entire thing. So this describes the case when one gluon emission is order 1, and another gluon emission is order 1, and another gluon emission is order 1, and they're all order 1. Last page, please. So basically, that means I have a bunch of corrections that look like this: alpha S log constant to the n power, and I have to sum them all from 0 to infinity. They're all equally important. There's a lot of details that go into this, but loosely speaking, what happens is you exponentiate that curve. And the exponential of a log is a power. This generally predicts that the number of gluons should grow like a power of the center of mass energy. This is sometimes referred to as a Regge trajectory. So this is the physics of small x. You have an abundance of gluon radiation. QCD loves to bram off more and more soft gluons. And if I go to higher and higher energies, I'm going to reach a limit of very high occupation number when I have a massive number of gluons in the problem. And that changes my perturbation theory. I'm not doing dilute QCD anymore, where each scattering is now a higher order. Now, multiple emissions are order 1. Multiple scattering on abundant gluons will all be order 1. This is a regime of dense QCD. And the effective theory of dense QCD looks very different than the theory of dilute QCD. So that's what I want to talk about tomorrow. The last point, I guess, is this one. You see this even in data. When you look at the particle production cross-section. So this is a measured number of charged particles at the LHC in PP collisions as a function of pseudo-rapidity eta. To a remarkable degree, it's a constant, and the theory predicts that it should be constant up to around the beam rapidity. As long as I'm far away from both beam rapidities, I expect to see a constant pedestal. Even the small saddle dip in the middle is actually still a constant. It's a function of the Jacobian between y and the pseudo-rapidity eta. So you see even in real life that boost invariance, or the rapidity independence, is a real feature of QCD. So resumming that in high energy QCD is the origin of color glass condensate and gluon saturation. So I'll stop here. Thank you for your patience. I know I'm over time.
Other than that, the book you referenced is very useful. I put a link in the Indigo so people can find that.
Perfect.
So yeah, that's really helpful.
Awesome. Thank you.
Excellent. Thank you.
Sure. Yes, please.
When you, I mean, it's long gone, but when you started doing, evaluating the diagrams for the corrections, diagrams A and B,
Yeah.
you already were excluding the mass fermions.
Yeah, that's right.
Okay.
I'm intending to work in the S going to infinity limit, so I know that masses should be negligible there unless I need it as a regulator for something. Yeah.
Just making sure.
Yeah, that's correct. Yeah, sorry, I know it came pretty fast.
abuse my position.
Sure.
So first of all, the diagram that you neglected, if you just,
The U channel?
the usual, you
Yeah.
just manage there and just write the answer, think, okay, I don't.
Mhm.
Using your methods, you can recover the usual U or T results immediately. Is the color factor would be appropriate?
Yeah, so like U channel squared should have the same color factor as T channel squared. You could have some interesting color structure for UT interference, I guess.
So now the fact that we have a soft growth radiation and it's independent of rapidity.
Yes.
You use the certain kinematics to.
Yeah, I didn't emphasize this, but it was crucial in the beginning that I was looking at the gluon K, which is being produced at mid rapidity, so that it's the plus momentum of my gluon is small compared to the big plus momentum of the problem and the minus momentum. So I'm working in the limit where my K plus is much, much less than the large P2 plus in the problem, which is like square root S. My K minus is also much, much less than P1 minus, which is of order square root S.
What I meant to say is that some data,
Ah,
there is always this plateau,
yes,
the mid rapidity, which people may conjecture come from this soft gluon radiation, which hadronizes.
yeah, that's correct.
So would you conjecture that this result is independent of your kinematics such that soft gluon radiation would always be occupying the whole rapidity space uniformly, or it's complicated?
Simple answer is yes. I would discriminate sort of two conditions. So one is S much greater than T. Then this is my kinematic small x or kinematic high energy. If I have this corresponds to boost invariance. So this is what sets in, let's say, x about 0.01 for sure. Even 0.1 probably is a good satisfaction of these kinematics. That's enough to give you boost invariance. But then if you want to say when do high density effects become important? When do I have to resum such things? Then you need to go to even smaller x than this such that you satisfy this constraint. This one requires that x is of order e to the 1 over alpha s, which is even smaller than 1. So this is x much less than 1. This is x even smaller than that. And so I'm trying to distinguish between this condition is easy to meet. Once I've satisfied this for all kinematics higher energy or lower x than that, then yes, you'll have that boost invariant pedestal. The open question is how far do you have to go further than that in x before I see unambiguously small x evolution, gluon saturation, all of that stuff. And we expect that to be even exponentially smaller in x.
Well, resonation everywhere. So it's once things happen. Algorithms which spoil your convergence become serious. And then what happens is that people write an exponentiation of these factors. And then the first term would correspond to the first term here.
Exactly.
So is it explicit you do the second terms calculation, so alpha is squared and actually see that it corresponds to the expansion of your exponential, or you just see the first term and you exponentiate it? So how it works technically?
So technically you have to construct a differential equation. And the crucial part about the differential equation is finding out when you generate the log and when you don't. So if I now have a correction to the diagram that I showed, so we did this one. If I now have another correction which looks like this, so now I have K1 and K2. We saw that I get a single log if my K1 plus is much less than P2 plus, my K1 minus is much, much less than P1 minus. It turns out that I can also get, maybe let me write it the other way. So this was minus and this was plus. My P1 minus is much greater than my K1 minus. So the crucial question then is if I have a second one, when do I generate a second log? So I get log 1 over x from this guy, I get the alpha s, and then do I or don't I get another log 1 over x from this guy? If I do that, then this continues to become a part of that iterated kernel. And the crucial part is that you show that you generate the second log as long as you preserve the ordering conditions. So as long as the first gluon is much harder than the second gluon, or the second gluon is much softer than the first. Then this gluon emission is independent of the details of where it came from. And then I just generate alpha S times. So much like DGLAP, there's a strong ordering constraint, an angular ordering constraint that says if I want to generate a log at every step as I iterate this kernel, I have to maintain a strong ordering and rapidity. So that I'm really thinking of T, Z. So if this is the rapidity of the collision, then the first emission has, I don't know, something which is soft compared to one of the light cone directions. The second emission has something soft compared to both of the previous ones, and then so on and so forth. I always have something which is softer and softer compared to all of the parents before. And as long as you satisfy that hierarchical ordering of the momenta, then you can show that you always generate alpha S log 1 over X n number of times, no matter how many times you iterate the kernel. It's always based on a leading logarithmic approximation. Yep, that's right.
So the people working with such an by, you know,
Yes, yes.
it was very instructive to see, you know, the way how you do it. Do you use the methods?
I don't use those frequently, but I've seen them used in the field. It's a useful tool. So this is the spin helicity formalism where you replace U and U bar. Yes, absolutely.
Any other questions before we go for lunch?
Tomorrow will not be a Blackboard talk. I'll go through some slides.
Have homework for them?
Homework? No, no homework.
They're done by.
Find my typos.
No homework. Perfect. All right. Let's thank.
Just a quick reminder, this evening at 7:30, we'll have our final discussion section, and both Matt